So most of you guys have had your lab this week, right? No? Oh, you got lab tomorrow?
Yeah.
Oh. But the brain lab should have been pretty damn easy for you guys compared to.
It was. I was so thankful. I was like, thank you, Melody.
So this is because I accidentally skipped skin.
Yeah.
That's why we're like a little bit ahead. I'm going to have to do that on purpose in the future. So we're also going to be a little bit ahead. The stuff that we're going to finish today will be the stuff that you do tomorrow. Well, tomorrow, because the first lab starts Friday, and then after spring break, which means you will have ample time to forget it all before the lab comes up. So, and then, did you guys all get your lab practicals back? Everybody good? You're all still here, which is, that's a good sign, right? A lot of times there's a lot of drop off immediately after a lab practical. What's your overall impression? Was it harder than you thought it was going to be? Reasonable, easier? Any feedback that you want to give me? About what you expected? Yeah. It's challenging just because there's so much material. Yeah. The second half of lab, I don't think is as hard. The second half of lecture is harder. So it's okay. It balances out.
I have a question.
Go ahead.
Longus fibularis, it was in like the practice midterm and my midterm and your exam. Like, is there some?
No.
Okay.
I didn't even know.
A special muscle.
No. It's easy to find on a picture. Easy to see on a cadaver. Sometimes the things you get tested on are the things that are easy to write clear questions about. So, like there's so damn many muscles here that like how do you make an image actually show those? So a lot of times I just let them ask most of these in lab instead of study. Okay, so we are finishing up the nervous system. And this set of notes is over chapter 16, which is spinal cord and spinal nerves, and then we skip to chapter 18, which is autonomic nervous system. This stuff you will be doing in lab Friday or week after spring break. This stuff you don't do in lab at all because it's so damn hard to dissect out, but you use it in phys, really a lot. You use it in phys. We are going to start with just the spinal cord. Oh, by the way, please remember that you are responsible for the cranial nerves on this test as well. You had time to find them in lab, and remember sensory, motor, or both, right? Sensory, motor, or both, and then know the names, numbers, and all of that kind of stuff. So that's gonna be on the next test, okay? What I don't generally do, by the way, on tests is ask you those cranial nerves down at the brainstem in an image because they do not look a damn thing like that in the actual wet specimen. But I mean, you should be able to find the optic nerve and the oculomotor and the olfactory nerve on any image. The ones at the bottom, I kind of have to do process of elimination with those to figure out which ones I'm looking at. So while I don't usually ask them off of an image, I'm not saying I won't ask functionality because I will ask functionality. Good? Just to be clear. Okay, so we're going to do spinal cord today. So the spinal cord, of course, is still part of the central nervous system, and it has a couple of different functionalities. First of all, most of the wiring that's coming from the PNS will go through the spinal cord to get to the brain, with the exception of the stuff that use like the cranial nerves, right? And then, so it's got to have white matter, right, wiring. And then in addition, the spinal cord also has gray matter because the spinal cord does some integration. It does some decision making, although it's completely subconscious and involuntary decision making. So just to show you what the spinal cord generally looks like, if you do a cross section of the spinal cord, you are going to see a gray matter on the outside, white matter on the outside, gray matter on the inside pattern, right? So I probably don't even have to tell you, what kinds of tracts do you think are disproportionately represented in the spinal cord? Yeah, it's mostly projection tract, not exclusively, but mostly projection tracts. And then the gray matter in the spinal cord is mostly going to be doing integration of really, really simple functionality like reflexes, and we'll talk about reflexes and stuff today. So it's not like solving calculus problems or anything. Okay, so let's talk about the basics of the spinal cord. we have this dissection on each campus. You should make sure that you get to look at this dissection. It's a really hard dissection to do. One of the reasons it's really hard is that in order to see this posterior view of the spinal cord, what you're going to have to do is to remove the lamina and spinous processes of all of the vertebra, even all the way down to the sacrum. And the sacrum does not want to let go. The sacrum is thick, thick, thick. But you have one of these dissections on each campus. In addition, they've removed the spinal processes, the lamina, part of the sacrum, and part of the occipital bone so that you can see the complete connection of the brain to the spinal cord and all the way out to the nerves. And then they've taken the dura mater, which completely encases the spinal cord, and reflected it back so that you can actually see this internal structures as well. So make sure that you take the time to look at that dissection. Okay, so the spinal cord proper begins arbitrarily at the foramen magnum. If you're above the foramen magnum, you're still considered medulla oblongata. If you're below the foramen magnum, you are spinal cord. If you looked at a cross-section of the bottom part of the medulla oblongata and the top part of the spinal cord, they look exactly the same. They're just continuous with one another. The spinal cord ends far higher than most people expect it to. If you can feel your last ribs down here, and I can, then count down 2 spinous processes. It ends about L1 or L2. That's where your spinal cord ends, which is why you never hear about someone having an L5 spinal cord injury, because it ain't down there, right? Okay, so it ends about L1 or L2. Now, I'm not saying that the vertebral foramen is empty after that, just that it's PNS tissue and not CNS tissue down there. Right? It runs, it's PNS tissue that's running in there. So it begins, it ends about L1 or L2. That means that on average, in most of us, it's around 16 to 18 inches long, but it depends on how tall you are. Like Shaquille O'Neal's doesn't end at T4. It goes all the way down to L1 or L2. The other thing, which I found really surprising once I finally started doing dissections, is that it's anatomically like unimpressive. It's only like a ½ inch wide, ½ inch in diameter. It's teeny tiny. I expect it to be like a big old freaking cable with like warning signs on it. But no, it's like ½ inch wide. Okay, now the meninges. This picture is trying to show you that the meninges actually extend beyond the end of the spinal cord. So this is showing you the dura mater, and beneath it would be the arachnoid. Okay, so they go down to about S1 or S2, and the pia mater actually covers this green structure and goes all the way down to the coccyx. That has some clinical significance, of course, because if the subarachnoid space is still down here, right? That means I've still got cerebrospinal fluid circulating, yes? That means that if I needed to see some cerebrospinal fluid, luckily I don't have to take it from around my brain or even around my spinal cord. So if I wanted to do a lumbar puncture or a spinal tap to figure out what the hell's going on, I go well below L2, usually between L3 and L4 or L4 and L5. And then I stick it through the dura mater into the arachnoid, right? And then suck up fluid from the subarachnoid space. And why would I want to do that? Because it's a good indication of what's going on with the central nervous system without actually taking a biopsy of the tissue. So for instance, let's say I thought you had some cancer and I took a biopsy and then I'm like, oh no, that was fine. You can't stick it back. Oh, I guess you need that. So first indications to try to figure out what's going on with the central nervous system is sometimes by a spinal tap. And they suck up the cerebrospinal fluid and then they can examine it for chemical content, what's the pH, how much glucose, oxygen, carbon dioxide is in it. Is that normal, abnormal, right? And then microbial content. Sometimes you will actually get microbes, either viruses or bacteria in the CSF, and you can tell directly what's going on. Sometimes they're not in the CSF, but there are increased numbers of white blood cells that can tell you what's going on. We haven't studied blood yet, but certain type of white blood cell increases in response to bacterial infections, different one to viral infections, still different one to eukaryotic animal parasites will increase. So it's a good first indication. And they can even use it as a first indication of central nervous system cancers, because cancer cells by their very nature do not stay put. That's why metastasis occurs, right? Because they break loose. So sometimes you can find abnormal cells in the cerebrospinal fluid to tell you what's going on. usually the reason they do spinal taps is because they think you have meningitis, right? That's the most common reason to do a spinal tap. Meningitis is either bacterial or viral, and it's treated differently depending on whether it's bacterial or viral. Okay, so now, exiting from the spinal cord are 31 pairs of spinal nerves. And let me just tell you about the numbering now so that we can refer to it later. They're not hard because they don't have like individual names. They're just named for where they come off. The general rule is that they are named for the vertebra above them, but the cervical ones break that rule because the first one comes out above the first cervical vertebra. It comes out between the first cervical vertebra and the foramen magnum. That means that how many cervical vertebrae do you have? 7. But you have 8 cervical spinal nerves, right? Because you got an extra one.
Okay.
Does that make sense? Okay. The numbering up there gets really confusing because you'll talk about having a C4, C5 spinal cord injury, and then the vertebrae are slightly different. So when we play with it, we'll have to practice that a little bit. I always have to count down. These, however, are totally normal because how many thoracic vertebrae do you have? 12. And there's 12 thoracic spinal nerves. So these are called cervical spinal nerves, and they're named and numbered C1 through C8. These are T1 through T12. Thoracic spinal nerves, L1 through L5. Okay, down here, how do you have spinal nerves when the spinal cord ends? Because they are named for where they exit, not for where they come off of, right? So these ultimately all came from this region of the spinal cord, but they didn't leave until they went down there. That makes sense? So L1 through L5, even though the spinal cord's still up there, S1 through S5, and then the last one is C01. You've got one coccygeal spinal nerve, and it's C01 because C1 was already taken. That makes sense? Okay, so, and we'll come back to these and we'll talk about the functionality of each one of them in just a minute. Okay. So let's look at the gross anatomy of the spinal cord just to make sure that you can find some big things. First off, this picture doesn't show it really well, so just trust me that it's true. The cervical region of the spinal cord is slightly wider than the thoracic region of the spinal cord. And then the lumbar region is plump or wide again, just a little bit wider. I mean, the whole damn thing is only half an inch wide, so it's maybe like 1/10 of an inch or something wider. It has to do with functionality. So can anybody hazard a guess as to why the cervical region and the lumbar region are slightly wider than the thoracic region? It's not the ribs, it's something about what they're innervating. The cervical region is primarily going to innervate what? Arms, yes. You need lots and lots of sensory and motor fibers going from, right? And the lumbar region innervates primarily what? Legs, exactly. So they tend to be just a teeny bit wider, okay? So that's called the cervical enlargement, even though it doesn't look larger. And then the lumbar enlargement. Why is this region not doing very much? Our region's not doing very much comparatively speaking because it's not going to the limbs. You don't have as much sensory and motor functionality here. And it's also not going to the ventral body cavity. Because do you remember which cranial nerve innervates the vast majority of the ventral body cavity? Vagus nerve. So I took care of the guts, right? And I don't have like sensory and motor function complexity. So primarily what the thoracic region of the spinal cord is doing is just innervating like the intercostal muscles and cutaneous or skin innervation here. We don't even have a whole lot of like capacity to discern what's going on here. So if somebody, like, you can't even tell where it itches in your own damn back, right? You're like, you're like running around, like, I know it's back there, but like I need a map. So there is not as much activity, right? And so it can be narrower there. Okay, so cervical and lumbar enlargement. Now, this one, the end of the spinal cord proper, which ends at L1 or L2, ends in a cone, little point. I'll show you another picture of it. So do you see in this figure how the spinal cord proper ends at a point? This is all like PNS tissue right up here. That is called the conus medullaris. It's the end of the spinal cord proper, and it literally means cone in the middle, conus medullaris. Okay, now when you are in lab and you're examining this, run your finger down the spinal cord and you can feel it end. You can feel when it stops being like solid spinal cord tissue and starts being just a wiring that's coming out from it. The nerves that extend after the spinal cord ends are called the cauda equina collectively. Cauda means tail and equine means horse, so it's horse's tail, yeah? They're really hip on the Latin words down here, okay? Because then we got one more. And one more is this green structure that you're seeing right here. And that green structure goes all the way from the conus medullaris, which is the end of the spinal cord proper, and attaches it down usually to the coccyx, sometimes to the sacrum, okay? That actually positions the spinal cord so it doesn't flop around within the vertebral cavity. And you can see it's always like slightly different in color. You can see it on the cadavers as well. And you can see it right here. So watch. Down the conus medullaris, and then do you see this one that's different color? Okay. What that is, that's not nervous tissue, that's connective tissue. It has the pia mater on the top of it, and it positions the spinal cord within the vertebral cavity. It's called the filum terminale, which means last hair. Okay, so enough Latin for you. Conus medullaris is the cone in the middle, end of the spinal cord proper. And that is what? CNS or PNS tissue? CNS. Cauda equina is all of the nerves that extend after the spinal cord ends. Is that CNS or PNS tissue? PNS. And then the last hair right here is not nervous tissue. That's connective tissue. Okay, filum terminale. Good? Okay, you can see all of those in the dissected cadavers that we have. There's one good spinal cord cadaver on each campus. Okay, so now the next thing that we have to do is the spinal cord in cross-section. And it is super easy. You have models in lab for this. The only issue is that you always have to be able to dependably tell anterior from posterior on a spinal cord in cross-section. And if it's like in the vertebra, it's super easy, right? Because of course the spinous process is always a posterior structure and the body is always an anterior structure. But what if it's not, right? You still have to be able to do it. There's several dependable ways. I'll tell you what I use. You can find whatever works for you. And the reason you have to be able to tell anterior from posterior is that all of the structures that you have to learn are labeled dorsal or ventral or anterior or posterior, whatever, right? So you get all of them wrong if you can't tell anterior from posterior. So I'll tell you the way that I do it. When you don't have the vertebra for orientation, I use this lump right here. That lump right there is called the dorsal or posterior root ganglion. It's a ganglion. We're going to find out its functionality today. And the anterior root never has one, ever. Okay? And then the other thing is the shape of the gray matter. The shape of the gray matter, it varies a little bit as you go from cervical to thoracic to lumbar region, but it has some consistencies. And the consistencies to me, in my mind, are that thing looks like a swallowtail butterfly to me, which the top wings are rounded and the bottom wings are pointy. And the pointy wings always point posterior. So the butterfly is flying forward. Does that make sense? Okay. So you can see the pointy wings. Even when it varies and the shape will vary a little bit, that's pretty damn dependable. So in this figure, what's posterior, top or bottom? Top. What's posterior? Top. Luckily, your textbook is very consistent about it. And then, but it's not always, what's anterior, posterior in this picture? Bottom. This posterior is bottom, right? So you don't know which way the model is going to be or any image that you run into, so you have to be able to sort of dependably figure out where you are with that. Okay, so there's a couple of other things that you will have to describe. If this textbook was a little bit more dependable about the figures, you could see that the anterior median fissure right here is way deeper than the posterior median sulcus, but they represented it completely backwards. So that's not really dependable on these figures. But the anterior one is deeper than the posterior one. Okay, so, let's do this one. Here. This is a histology slide. Can you tell anterior from posterior? Where's posterior? Yeah, posterior is up. Right. Good? Okay, so Now, let's find some structure-function relationships and make sure that we can see a few things. So when we're looking at these figures, this is called the posterior or dorsal root ganglion. I don't care if you use dorsal and ventral or anterior and posterior. This textbook uses anterior and posterior. I'm in the habit of using dorsal and ventral because it's how I learned it, and neither one is incorrect. Okay, so don't get frustrated with me if it says anterior and I say ventral. Okay, so the dorsal root ganglion. What is in here, by the way, to make this make sense with the stories that you've already learned this semester, is the cell bodies of sensory neurons. Somebody sent me an email asking me about like where your sensory receptors were and where the neuron cell bodies were, because they got confused when they were thinking about sensation and in motor out. They were thinking that the neurons had to be multipolar neurons, which means the cell bodies would be out here, which doesn't make a whole hell of a lot of sense. They wouldn't be protected. So how do you get around that whole thing? And the reason I didn't reply to you was because I knew I was about to teach this to you. So here you are. Here's your answer. Okay, so if I am doing sensation, this neuron is close to the spinal cord. It's actually slightly protected by the bone, just so you know. What structural category of neuron is that? Yeah, that's a unipolar neuron, and it ends up close to the spinal cord and relatively well protected. Does that make sense? That's what's in the dorsal root. So the dorsal or posterior side of the spinal cord is going to have sensory functionality, and we will see that the anterior portion has motor functionality. So what's in the dorsal root ganglion is the cell bodies of primarily somatic sensory neurons, and then what kind of support staff? Glial cells will it have? Yeah, satellite cells will be in there as well. Good, and we'll come back to that. We're going to do this figure in detail in just a minute. So the function of the back half of the spinal cord is primarily sensation. Okay, and then the ventral or front half of the spinal cord is primarily motor activity. So sensation in through the back, motor out through the front. Okay, go ahead.
So is that unipolar neuron? Are they connected, or is there just one?
There's one.
All the way to the spinal.
All the way from the sensory receptor to the spinal cord. Yeah. Okay, so the ventral root never has a ganglion. That'll be important. And the cell body for the axon that runs through this root will generally be in this part of the spinal cord. Good? And the gray matter of the spinal cord. Okay, and we're about to learn the parts of the spinal cords. So let's look at the spinal cord in a little bit more detail. Okay, so when you look at a cross-section of the spinal cord, you can basically describe the gray matter and white matter arrangement. It's not very hard at all. When you do a cross-section, it just looks like regions when you do a cross-section, but isn't actually this a column of like fibers? Okay, so do a cross-section of the spinal cord. You can describe the white matter in 3 or 4 different places. This is the anterior white column, or this textbook uses the word funiculus. I know which one I would try to remember. Anterior white column. Posterior white column, and both of those terms are on your lab list, funiculus or white column, because I thought funiculus was dumb. No other textbook uses that. Posterior white column, and then lateral white columns. Yes? Okay. Now, and then one little thing that's neither anterior nor posterior nor lateral is the part that connects the two sides. That part, I won't be surprised, is called the white commissure. Yeah? Okay. So as long as you can figure out which anterior and posterior, you got all of those golden, right? And then the gray matter is not called columns, it's called horns, or sometimes gray horns. And it's not too bad either. You've got anterior gray horns, right? You've got posterior gray horns, which is the bottom wing of the butterfly. And then sometimes you have easily distinguished lateral gray horns. But the shape changes as you go down. So don't be at all surprised if you look at a different picture and you don't see like the lateral ones being easily distinguished, right? But you can still see the anterior ones and the posterior ones, right? This part where the gray matter connects side to side that has the central canal in the middle, that is called the gray commissure. And you don't usually see commissure used for gray matter, but it's gray matter that connects the two sides, so they just call it a commissure. Okay? All right. So let's just make sure that you can do it in a histology image. Okay, so tell me what this is. Anterior white columns, right? Posterior white columns, lateral white columns. What is this? Anterior horn or gray horn. Lateral gray horn, posterior gray horn. How about here? Gray commissure. That little guy right there in the middle is the central canal of the spinal cord where you have cerebrospinal fluid. Good. And what's this region right here? White commissure. Good. So it's not hard, right? As long as you got the regions, you're good. Okay. So now let's put it together with functionality. Okay. So let's figure out how this would actually be used. Okay, so I want to talk about what we call a spinal reflex. And a spinal reflex is really like just this stimulus response behavior, and it doesn't involve your cerebral cortex. So if, for instance, I went up to Allie and I said, Allie, will you hand me your pencil? And she handed me your pencil. This is a voluntary activity on both of our parts and it involves the cerebral cortex. That's different than a spinal reflex. The spinal reflex is way dumber than that. A spinal reflex would be like stimulus with a dependable response, right? And it doesn't involve my cerebral cortex. It's way faster than a voluntary response, but it's kind of a one-trick pony, right? At the most, it has the capacity of on or off, 1 or 0, but it doesn't have any complexity of activity. So we are going to do a spinal reflex from this image in which you poke someone with a pin and they respond by twitching, right? You poke them with a pin and they respond by twitching. Maybe you poked them in the hand, I don't know. And these things even work when a person is brain dead, right? You can still have reflexes when a person is brain dead. So what we are going to do here is we're going to learn the parts of this thing that's called a reflex arc, okay? And it starts with a sensory receptor, right? Generally, we're going to be using touch, temperature, pressure, pain, and we're going to be talking primarily about somatic sensations that we're dealing with here. So we're going to poke someone with a pin, and then let's learn the structures and the functions on our way in. As we are on our way in, we go up the dorsal or posterior root, right? And we find the neuron cell body of that sensory neuron in the blank blank ganglion. What is it? Posterior or dorsal root ganglion. And the axon runs through this with it, which is the dorsal root. Does that make sense? Okay. And then sometimes there is a decision maker called an interneuron in here. This one is one in which it's just got a 1 or 0. It can say, I'm going to send the stimulus on or I'm not going to. But sometimes you don't even have that. Sometimes you have a monosynaptic reflex in which the sensory input is always met with exactly the same motor output, and therefore you don't need a switch in the middle. Does that make sense? So this one is showing you an interneuron, but this activity right here, that doesn't even need a neuron in the middle because it always responds exactly the same way to the stimulus, right? Okay, so sometimes you have an interneuron in the middle. If you do, it's going to be in the gray matter because it's a neuron of the spinal cord, right? Okay, so whether you have it or not, the cell body of the motor neuron, this one's going to be a somatic motor neuron, is usually going to be in the anterior gray horn, yeah? And it's going to send out the motor information down the axon through the anterior root, right? Back out to the effector. Good? So that means that somebody pokes me with a pin, it goes in the back side of my spinal cord, out the front side of my spinal cord and back out. That's what's happening there. Got it? Okay. That's why I told you guys that like the only way that and still I don't do it right every time, but the only way that I can like remember the whole post-central gyrus, pre-central gyrus thing is that it's the same as the spinal cord, right? Because I have sensory on the back and motor on the front. But I really liked yours, which is touchy. Weren't you the touchy-feely guy? I mean,
touchy-feely.
Sorry, I didn't mean it that way. But I really liked the touchy-feely. It helped me remember. So touchy-feely, yeah. Anterior to posterior touchy-feely. I'm going to use that forever from now on. Stealing is just figuring out what is really effective, or teaching is just figuring out what is really effective to steal from other people, right? And then present it as your own clever intuition. Because I'm never going to give you credit, just so you know. But I will say, this student. By the way, how did you do on your lab practical? Did you do okay? You were really worried.
I did fair.
You did fair? Not as bad as you thought? Good, I'm glad. Okay, so the flow of information through a spinal reflex is through the spinal cord only, and it's super duper fast. It's kind of a one-trick pony, arguably two tricks, right? On versus off. Now, what about your cerebral cortex awareness of it? Because you do send up an action potential to your cerebral cortex to tell it what was going on, but it's really like asking forgiveness, not permission, right? It's like you steal your parents' car, and you bring it back and you hand them the keys and you say thanks, right? The decision was already made and you weren't involved in the process. However, I am going to let you know that it occurred. It's like putting your hand on a hot stove, right, and responding to it. Your cerebral cortex still needs to know that there's a damn hot stove there, right? So you don't have to do that over and over again, right? So it sends up a flag to your cerebral cortex. It actually happens slightly behind the reflex, right? So the reflex is going on at the time that the cerebral cortex becomes aware of it. Is that interesting? Yeah. So it's actually...
It's that. I actually have a funny... Sorry.
Go ahead. No, go ahead.
Of that. I get really nervous. I'm at the dentist. And so my reflex one time, she was like hitting a nerve in my... I like pushed her away. And afterwards, I'm like, oh, I'm sorry. I didn't mean to do that, but it's like that after.
So you're going to need hazard pay when you become a dental hygienist, right? I've got two friends who are dental hygienists, and they say it's a terrible, terrible job. Like, nobody is ever happy to see you, ever.
Never.
Ever. And you have to constantly reprimand people about their hygiene, right?
Isn't it one of like the highest depressed and like highest suicide jobs in America?
Is it really?
I think it's in front of.
Why would you kill it?
It's in front of.
I mean, people are gross. Maybe that's why.
Yeah.
Really? I'm going to look that up.
Well, and you can't really talk to your people. Like
They
they're
still
out
do,
of school.
That's an interesting thing. And both of my friends who are dental hygienists are trying really hard to figure out how the hell to get out of doing it.
Wow.
Yeah, they don't want to do it anymore.
I wonder how many dentists have a they have like their own dentist or a
Oh, I love that stuff. That stuff's amazing. I love going to the dentist. I didn't have any bad experiences. I think it's because I grew up really poor and I never got to go to the dentist. And then when I finally was able to have medical insurance and go to the dentist, it makes me feel like I'm decidedly middle class. I'm like, I'm going to the dentist like a grown up.
What now?
I'm gonna buy an extra pack of toilet paper too.
But you don't tell your friends how excited you are.
What?
You don't tell your friends how excited you are. Though.
I love going to the dentist. I get my teeth cleaned as many times as I can.
I just have to tell myself the whole time not to punch.
Don't punch anybody.
My
You should,
reflexes are really aggressive.
you should medicate yourself. Okay, so now let's go to the branches of the spinal cord. So this is where people get a little confused, so I want to make sure if you weren't paying attention before, you are now. Okay, so what we just said, so stick with me, what we just said was that the dorsal root has what functionality? Sensory, and the ventral root has motor. Okay, so now stick with me as we put this together. The dorsal root right here, okay, and the ventral root, okay? That's the dorsal root ganglion, so we've oriented ourselves. When you put them together, right here, it becomes a spinal nerve. And we know what a spinal nerve is because we have 31 pairs of spinal nerves, right? Those are what leave the spinal cord. Now, with that in mind, that means that the spinal nerve must be what in functionality? Sensory, motor, or mixed? They're all mixed, yes. All spinal nerves are mixed in functionality. Good? Because they have axons from sensory and axons from motor. Okay. But now, they're going to immediately split. And this is where students get irritated. So this is a dorsal root, and this is a ventral root. This is a spinal nerve, yes? And then they are going to immediately split. And when they split, they are no longer roots, they are rami. Plural of ramus, which means branch, okay? This is the posterior ramus, note how tiny. This is the anterior ramus. We won't learn this one. This one's part of the autonomic nervous system. Posterior ramus, anterior ramus. Okay, so when they split into rami, it's based on where they're going, not what they're doing. So they stay mixed in function. Okay, so we're going to practice this a little bit. That posterior ramus innervates sensory and motor function posterior to the spinal cord. And there isn't a whole hell of a lot back there, is there? Do you see there's just a little bit of musculature and sensory activity? So notice how small that one is compared to this one. Yes? The anterior ramus innervates sensory and motor function for everything that you haven't already innervated. You already did like the abdominal pelvic cavity. Everything that you haven't innervated anterior to the spinal cord, including your limbs. So do you see why that one's so much bigger? Okay, so with that in mind, here's your posterior ramus and here's your anterior ramus. Okay, so what I want to talk about is I'm going to give you two different examples for you to play with this terminology. Okay, so the first one, what I want you to do is I want you to tell me the structures I'm going to go through as I respond to an itch on my back with a twitch on my back. Okay, an itch on my back. So I've got an itch on my back. What's the first structure on this figure that I'm going to go through?
The anterior.
Not anterior. Posterior ramus, and then through here, which is spinal nerve, right? And then dorsal root or posterior root, ganglion, and root, yes? And then through which portion of the gray matter? Posterior gray horn. Then anterior gray horn, and now send it out where? Anterior ramus, back through the, anterior root. Sorry, I was testing you. You did great, Charlie. Anterior root to spinal nerve, and now where? Not anterior ramus. I'm twitching. Posterior ramus. Okay, now I'm going to do something different. This time I'm going to put my hand on a hot stove and move my hand. You ready? Okay. Hand on a hot stove. Comes through which? Anterior ramus, then spinal nerve, then posterior dorsal root and the ganglion, then gray matter, posterior, anterior gray horn, and now anterior root, spinal nerve, anterior ramus. Does that make sense? That's how that whole story goes, and you can put it. Does that make sense to you guys?
Yeah.
Okay. So obviously the most common thing for students to do is to mix up roots and rami. Okay. So what if I asked you a question about the dorsal root or the dorsal ramus is sensory? It's the dorsal root that's sensory, right? Does that make sense? Yeah, the ramus is mixed. That makes sense, that functionality. So you have to practice just a little bit, run through it a few times with an example so that you can get it, okay? This is, we're going to talk about these in the next chapter, but they don't really fit into the story very well because it's primarily autonomic innervation, and we were just talking about somatic. Go ahead.
I have a silly question. So, just in between what looks like the dura mater and the bone and vertebrae, is that, it looks like adipose?
It is.
Connected tissue?
It's adipose connected tissue. This is the epidural space right here. And it's adipose and loose areolar connected tissue that serves as padding for the spinal cord. That's the epidural space. Good? Okay. So, okay, we did spinal nerve, we did all of that. Okay, so now what we are going to do is we are going to look at the spinal nerves and the branches that come off of them. Okay, so we already talked about numbering of the spinal nerves, C1 through C8, T1 through T12, L1 through L5, S1 through S5, and C01. Okay, so when we are looking at this picture, I want you to try to orient yourself. When we're looking at this picture, what they had to do is they had to cut off the lamina and the spinous processes, right? And so which thing is removed in this picture? The posterior ramus or the anterior ramus? Posterior ramus and everything that it came from. So you're not seeing any of the posterior ramus here. But that's okay because, of course, most of the innervation comes from the anterior rings, right? Okay. So all of these structures that you are going to see is actually branches off the anterior ramus of the spinal nerve. Okay. Okay. So remind yourself, spinal nerves, yeah, and then start looking at how the spinal nerves come out and give rise to nerves that kind of wad up. And so do you see this little wad of nerves that's right there? That's called the cervical plexus. A plexus is like a little collection or wad. Wad is not the technical term, but it always just like a little tangle of nerves. Yeah. So that's the cervical plexus. So they're usually named for either where they are or where they're going. This one is the brachial plexus. This one doesn't form a plexus. They don't wad up, right? They just run parallel to one another. Primarily what these are going to do is to give rise to innervation of the intercostal muscles and some sensory innervation in those regions. And then if you start moving down, this is the lumbar plexus, yeah? And then this one is the sacral plexus, and there's no coccygeal plexus. Good? Okay, so what we need to do now is we need to learn some important nerves out of each plexus, okay? And also how to identify a plexus when you see it, okay? So what I don't generally do in lecture is make you identify, you know, this nerve out of the plexus, because it's not going to look like that in the body. So that's a better thing for you to do in lab, okay? But you should be able to tell me that this is the cervical plexus. So here's a cervical plexus from a posterior view. Now let me show you from an anterior view, since primarily you're looking at the anterior rami anyway, okay? So it should be pretty damn easy for you to find the cervical plexus because you can see the atlas and the axis, right? So the cervical plexus primarily comes from about C1 through some of the last fibers are C4 or C5, and there's a little bit of variability there, okay? So you see this wad of nerves. Mostly what that wad of nerves is doing is sensory and motor innervation of like the neck region and the bottom of the head. And then we've just got a rogue, this guy, which comes from the cervical plexus. This one is the important nerve here. This is called the phrenic nerve. Why is that one super important? Innervates the diaphragm. So that one comes all the way from up here and goes down to the diaphragm. You actually have two. You will find that in the cadavers, but you won't generally find it up here. You will find it from the diaphragm and follow it back up. Does that make sense? Okay. So that's the phrenic nerve and the phrenic nerve innervation. So if you look at these, I won't ask you individual ones, but you can see that like the last cranial nerves kind of get wadded up in here too. So we don't have to worry about those. Greater auricular, it's like sensory and occipital, and like we've got the cervical nerve, so you can just kind of see where those are going. The only one that you have to know out of that for both lecture and lab is the phrenic nerve, okay? But you should be able to recognize that that's the brachial plexus. Good? Okay. By the way, I'm going to make a correction. I don't ever test off of this, but just so that you will know. Let's see, where were we? There we go. The phrenic nerve, the experts are arguing as to whether the phrenic nerve has any sensory function at all. Now, I know the plexus does, and the actual spinal nerve does, but some textbooks say that the phrenic nerve has only motor function to the diaphragm, and some say that it has some sensory function from the thoracic cavity. But if I were you, I would probably cross out the sensory function because it seems as if the evidence is piling up that it's primarily a motor nerve, or almost exclusively almost all the time a motor nerve. I never asked you that because the diaphragm thing is important enough that you'll remember it. But you can cross out that sensory function from thoracic cavity. I was just like trying to read and figure out what the current thought is on that, and they think it rarely has any sensory function. Not that it matters that much. Okay, so let's talk about, of course, your diaphragm is your primary muscle of respiration, right? Let's talk about spinal cord injuries. If you had a spinal cord injury and you lost control of your diaphragm, then of course you're going to die unless somebody puts you on a ventilator really quickly. What I want you to do is look at the anatomy and figure out where you would have to damage your spinal cord in order to lose control of the diaphragm. So this is C1, C2, right? C3, C4, C5. So remember that the vertebra is slightly below, right? Okay. C1, C2. Okay. So if I had a low spinal cord injury, no problem with the diaphragm. I mean, you're still screwed, but no problem with the diaphragm, right? Injure it up here. You can see that some of the fibers sometimes go to the phrenic nerve. So what you might have is loss of contractile strength or weakness in the diaphragm. Okay. Injure a little further up, right? Injure between C4 and 5 right here. Okay. Then you can see that you would lose the vast majority of your innervation right here to the phrenic nerve. And then injure one more vertebra up, right? And you would see that you would lose all of this, right? If you injure all the way up here, you are screwed because almost all of the fibers that go through the phrenic nerve come from up there, right? So I think Christopher Reeve's injury was C3, C4. I can't remember, it was either 3, 4, or 4, 5. And so he was on a ventilator the vast majority of the time. He could be off the ventilator for a few minutes and then he had to go back on the ventilator. Of course, remember that those are especially heinous injuries because you also obviously lost control of your intercostal muscles, which helps you breathe as well, right? So if you lose that and you lose partial innervation of your diaphragm, you're going to have problems. He eventually, like 15 years after his injury, flew over to, I can't remember which Scandinavian country, and had embryonic stem cell implants. And he got some reinnervation, but he had so much scar tissue that even though he regained a little bit of functionality, he didn't regain much of it. So does that make sense to you guys? Okay, so now the brachial plexus is the one that you will be most challenged by in lab. And there are a few of you guys who have lab tomorrow who are actually doing this in lab tomorrow. I'm going to explain it to you in lecture, but it's one of those things that doesn't really stick until you see it 3D. But maybe you'll remember the explanation once you finally see it 3D. So if you get lost, it's okay. Maybe it'll pull up something when you're actually in front of the cadaver. So this is the brachial plexus, and it's the brachial plexus because it goes primarily to the arm. It starts about C5 and it ends about T1, okay? So how do you find it? Well, you don't see an atlas or an axis, so it can't be cervical, right? But you do see the first rib, yes? Okay, so that's going to be the brachial plexus. When you are in a cadaver, almost invariably, you are going to find it in the armpit. So you're going to open the cadaver's arm and you're going to look in, and you're probably going to need to have somebody hold it out for you so that you can really see what's there. So it's going to run from this region down and through the armpit. And it looks like a big freaking mess, especially since it's not just nerves, it's also arteries and veins running through there. So the first thing that you need to be able to do is you need to confidently be able to tell a nerve from an artery from a vein. And some of you guys already know how to do that, but some of you don't. How do you do it if you do it? Anybody know how you tell them? Go ahead.
Veins are empty. They don't have any muscle on the walls.
Arteries and veins are empty, exactly. So arteries and veins, if you run your fingers through them, they're hollow and they'll sort of roll around on one another. FYI for later, an artery has more elasticity in the wall and it'll stand up, and a vein is really flat. It's got a very thin wall. What about a nerve? A nerve, when you run your fingers through it, it's not hollow. And if you are careful and have a good nerve, you can actually feel the fascicles inside. You feel like wiring within the wire. Does that make sense? Okay. So you have to find the nerves first and then just sort of get the other things. After you get used to it, it's easy to do it visually, but you sort of have to like teach yourself that. Okay, so you are going to be in here. And they've got them labeled here, but it doesn't do you any good because they're not going to look like this, right? I mean, it's fine to label this on a cadaver in a figure, but since we have real cadavers, you actually have to be able to find a way to find them in a real cadaver. So you know more nerves, or you are going to be responsible for more nerves out of this plexus than any other. But there are some that you can get out of the way really quickly. First off, this guy right here doesn't get in the rat's nest. This guy right here is called the long thoracic nerve, and it actually runs onto the chest wall. So you just find it on the chest wall. Okay? There are two more that aren't shown here, but I'll tell you where to find them because they're easy too. They're not part of the rat's nest either. They're the medial and lateral pectoral nerves. Here's how you find them. You find the pectoralis major and you flip it back, okay, and you see the minor. There's a nerve that goes under the minor, and that's the pectoralis, the medial pectoral nerve. And then there's a nerve that goes between the minor and the major, and that's the lateral one. So it's medial and lateral, right? Okay, so those are really easy to break, so be careful with them. If you pull the pectoralis major and minor too hard, you'll pop those nerves, okay? Which to me doesn't mean I won't test off of them. It means it's going to be harder for you to get the answers right. I've had students many, many times try to break things on the cadavers so they won't be tested on them. I will super glue the hell out of something just to put it back together. Oh yeah, people do that. It's terrible. They're like, I'll just break that nerve so I don't have to be asked it. Don't ever do that. That person got kicked out of lab too, by the way, for doing that. Because they actually told somebody they were doing it on purpose. And somebody was like, what? Dude, go ahead.
I have a question. When people have clogged arteries from the back, can you feel it?
Oh, yes. It's amazing. What?
Gross.
It's super gross and super amazing. So I'm so glad you asked that question. It's not relevant at all, but I'm going to tell you the story. So when we get cadavers who are smokers, a lot of times you can tell from the lungs, but this is terrible to tell you guys, but you often can't tell the lungs of a person who's lived in the valley from a smoker. They look very, very similar.
Yeah, it's crucial at another campus. We're like, oh, is he a smoker? His lungs were like black. Like, no, I just lived his whole life.
Yeah.
Oh, okay.
This is terrible. It like pains me as a parent to think about it. But so sometimes you can't tell whether the respiratory system looks like that because of smoking. But what I can always tell with a smoker is the blood vessels, the arteries. Because smoking, they think that it's because smoking removes the antioxidants from your system, and oxidized cholesterol sticks. So smokers have outrageous predisposition for arteriosclerosis and atherosclerosis. So every time I get a smoker, first thing I do is cut open an artery and squeeze it, and it's like a tube of toothpaste. It just squirts out.
Have you ever seen
Super
the
gross.
smoking?
What?
Have you seen the commercials? Squish.
Yeah, that's what made me want to do it. I was like, oh, now let's squirt. It's just like toothpaste. So, as if you needed another reason not to smoke. There's one for you. Okay, so now, what?
Just the little Gogurt tubes. I've never.
Oh, yes. Exactly. And it's all yellow, too.
That's so gross.
Fat retains its color like nothing else. It's just all yellow and bleh. Okay, so let me teach you about these other nerves. So we have the long thoracic, and then we have the medial and lateral pectoral, which you can't see in this figure, but you can see when you open the muscles up. And then how about this wad? This freaking mess. So I'm going to teach you this, and you will not quite get it until you see it in person. But I'm going to teach it to you for the first time. Okay, so first thing is there are 5 nerves that you will need to learn that's in this rat's nest. Okay, but let me show you how you find 3 of them, and then the other 2 get really easy because then it's just process of elimination. Do you see this M? Up, down, up, down. Do you see that M?
Yeah.
Okay, so that's 3 really important nerves. You have to, by the way, not just look for the M, you have to make sure it goes all the way up because it gets to be a mess up here. So make sure you follow it up and find the branch and then follow it back down, follow it back up. Okay, so the M, this would be on the right arm in the armpit that you were looking. The M gives you 3 of the nerves. The first one is the musculocutaneous. The middle of the M, conveniently, is the median nerve. Thank you for being easy for a second. Okay. And then the most medial of the nerves is the ulnar nerve. Okay, so we got the M, and then we'll add in 2 more. FYI, what you will have to do during Fridays and the next lab is that all of those muscles that you learned before, what used to be true, and I changed it with the last revision of the lab manual, is that there was another column on the muscle table. It was muscles with origin, insertion, action, and innervation. What I did is I took the innervation out of that lab and put it into the nerve lab because the muscles are hard enough. But now what you have to go back and do is you have to figure out what the ulnar nerve innervates. How many muscles that you learned. You're only responsible for muscles that you learned on the lab lists, okay? So you're gonna go put it together, and it's gonna make, a lot of times it's gonna make a lot of sense. Like a lot of the lateral muscles will be innervated by the ulnar nerve, and the medial muscles will be innervated by the radial nerve. And so that's going to be something that you are going to have to do. I do have to tell you, just so you know, and I'm gonna change this with the next revision over the summer, that because of that history, because the innervation used to be in the muscle lab, and then I moved it out, and now it just has named the muscles that this nerve innervates. And it kind of gave the students the impression that those nerves were motor, but they're not. They're mixed in function. So you, this semester, do not have to memorize their sensory functionality, but for instance, next semester when I rewrite the list, in addition to figuring out that the radial nerve innervates a lot of the lateral musculature, you will also find out that it innervates sensory function of this side of the hand, which is not that hard, right? So eventually it'll be added back in, but it isn't for you guys. So I'm just telling you that because I don't want you to have the impression that we're talking about motor nerves here. These are, with only a couple of exceptions, these are all mixed in function. Everybody good? Okay, so you got your M, you've got your musculocutaneous, you've got your median, and you've got your ulnar. What about the other two that you have to learn? The other two that you have to learn are right here, but they don't look like this on the cadaver, okay? What they look like on the cadaver is if you take that M and you pull it up, deep to that is these two nerves, okay? One of them is short, relatively thin, it's thinner than this one, and dives straight into the armpit. And that one's called the axillary nerve, right? So it's deep to the M, dives straight into the armpit, it's relatively thin. That's the axillary one. And then the other one is thicker, and you can see it for longer, like it's running for longer, okay? And you can't see what it's doing except on a couple of the cadavers. That one is called the radial nerve, and it runs in the armpit behind the M, and what it's doing is it's going to dive under some muscles and come out on this side. That's the radial nerve, okay? So all you have to do is really find the M and then tell these two apart from each other, which isn't that hard. This one dives straight into the armpit, and this one runs a little while and then goes lateral. Does that make sense? Okay, so the radial nerve on at least one cadaver, I don't know how many, we have it dissected out, the radial and the ulnar, so I love it when I can get this working, but sometimes it destroys structures in the process. We have it so that if you pull on the radial nerve here, you can see it come out down here. You can like pull on either side. Same thing with the ulnar. If you pull on it up here, you can see it all the way down to here, okay? It's hard to get them out without destroying the forearm muscles, but when I can, like I get them, so you can kind of prove to yourself. And one of the cadavers, at least one of the cadavers, you can pull on the phrenic nerve and see it in the cervical plexus too. So, so pull gently, don't yank. Just pull with a little suggestion of a tug and see if you can see it wiggle. So with that in mind, you have 3, 4, 5, 6, 7, 8. You have 8 nerves in the brachial plexus. But they're not that hard because one of them you find on the thoracic wall, 2 of them you find on the pectoralis, you've got your M and then the other 2, okay? And by the way, make sure that you look at more than one cadaver for the brachial plexus because there's a little anatomical variability. Like sometimes the blood vessels run under and sometimes they run over. So you can't like memorize without getting some experience. But if you can find the M, you can do it anytime. Okay, the thoracic spinal nerves are next. And the thoracic spinal nerves do not form a plexus. Primarily what they do is they give rise to the intercostal nerves that innervate the intercostal muscles. And then they do sensory innervation here too, somatic sensory innervation. So those are relatively easy, not hard to do at all. They're pretty easy to see on the cadavers too. And then the lumbar plexus. So let me show you where you would find the lumbar plexus and how to recognize it. The lumbar plexus is pretty easy because you do process of elimination. Because if it's cervical plexus, you can see the atlas and the axis, right? If it's the brachial plexus, you can see the first rib. Yeah? Lumbar plexus, you're not going to see any of that. And then the sacral plexus, well, you can see the sacrum, right? So you got that, okay? So here's what the lumbar plexus does. The lumbar plexus comes out L1 through L5. Only a few fibers come out L5. And then it dives anterior to the os coxa. Do you see that? dives anterior. And to oversimplify, primarily what it's doing is it's innervating the anterior portion of the thigh and the medial thigh and a couple of other things, okay? And then the other plexus will go posterior and we'll take care of the other stuff. So you only have to know 2 nerves out of here, and they're pretty damn easy. You can see what it does, like genitofemoral and stuff. But the Obturator Nerve, do you see it right there? You would find this one in a cadaver because you're coming out of the lumbar region and it's staying medial because it's running through what? Obturator foramen. You won't be surprised that it actually innervates some medial structures, medial muscles in the thigh, right? And then this guy right here, if you follow, let's see, where's it labeled right here? Oh, femoral. You follow the femoral nerve right here. It comes out of the plexus. It goes under the inguinal ligament, and then it innervates the anterior thigh. Does that make sense? So really it's super easy because you just got 2 nerves right there. You've got the obturator and the femoral. The femoral branches a whole bunch, but you're not responsible for any of the branches. So any nerve that's on the anterior thigh is femoral. It's fine, right? Even though it's a little bit of a lie because it branches into a million different nerves there too. Okay, so those are all the ones that you have to know out of that plexus. In some cadavers, by the way, we have this plexus dissected out from an anterior view, and in some it's a posterior view, so make sure you look at both, okay? And then the last plexus you should always be able to identify because this is the sacral plexus, okay? And the sacral plexus is the other one that you have to know a few nerves out of. Primarily, you've got these superior and inferior gluteal nerves. Those are hard to find on the cadaver. You don't usually find them at the plexus. You usually find them on the gluteal muscles. They're between the maximus and the medius, but if you pull it apart too hard, they get popped. So you can also see these really well on the new leg models that we just got like 2 weeks ago. I don't know if you've seen them. We've got some beautiful new leg models, and they have the superior and inferior gluteal nerves on them. And then, so these 2, and then this honker, which is the biggest nerve in the body, that nerve is enormous. So usually, because this, so look here for just a second. Do you see that this one starts out in the sacrum and then stays posterior to the os coxae? Okay, so this one goes posterior. So usually when you're looking for nerves from the sacral plexus, you're going to be looking at the cadaver from the backside. Good. So the sciatic nerve is the biggest nerve in the body. This guy right here, super easy to find. If you can't find that one, you should pretty much flunk that one. Okay, that is the sciatic nerve. It runs on the backside. The sciatic nerve will not immediately. It will split about knee level in most people into the tibial nerve and the common fibular, and you can kind of see where they're going. So the tibial nerve is going to stay medial, right? And the common fibular is going to go lateral. Should make sense, right? And then the common fibular splits into the superficial and the deep fibular. And that's not very hard either. Okay? So you spent all this freaking time so that by the time you got to deeper structures, everything actually made a lot more sense. So all of the work that you did before ends up making the more complicated labs not quite so difficult. We should dissect that out. And then the only nerve that you guys need to know that is not on your lab list yet is the pudendal nerve. And the reason I want you to know the pudendal nerve is because I promise you it's really important to you. It's this little guy right here. And the pudendal nerve does 2 things. Its motor function is controlling your sphincters. Thank you. I'm really glad it's there, aren't you? Right? So you don't pee and poop yourself all the damn time. Okay? So that's the pudendal nerve. You know what? One of my students told me in phys just the other day. He told me that he did a lie detector test for the Secret Service, and they make you sit on something that assesses the state of your sphincters during the polygraph test. And they told him that his sphincter was really close enough, so they thought he was lying. Apparently, you like close up your damn sphincters when you're lying. I know, I had no idea. I always knew that they did tons of other stuff with polygraph, like skin conductivity and pupil dilation and heart rate and respiration. But he said I had to sit on this thing that was like a mouse pad with electrodes. Go ahead.
Well, maybe that's why he's clinching, man.
I mean, so would it have something to do with the sympathetic nervous system?
It does. So this isn't only somatic function. It's also autonomic. But yes, it's the sympathetic nervous system. Yeah.
It'd be the involuntary sphincters, not
Yeah. Well, yeah, it is the involuntary sphincters. Yes. So he was like having involuntary contraction of his. Yeah. But also your somatic functionality changes when you're stressed as well.
Yeah.
So it has parallel changes as well. You've got a predictable somatic functionality and sympathetic functionality as well.
Okay, so
You get an
it's-
increase in muscle tone, for instance,
Yeah.
when you're lying, and that's somatic.
Yeah.
So they just work together. So I know the sphincter thing. Now I want to
Why didn't we
see.
evolve to lie better?
What?
Why did we evolve to lie better?
Why didn't we evolve to lie
That's
better?
You know, like,
Are you gonna say
It's
cats
like-
are better at lying?
What?
well, I mean, it's advantageous to be able to lie really well, right?
It depends on what you're trying to accomplish. Being able to lie really well is pro individual and antisocial.
Yeah, that's true.
That's huh?
Mental illness.
Yeah, mental. Ted Bundy, who was a sociopath, took 3 lie detector tests before he was caught because of physical evidence. So if you're a sociopath, you're an amazing liar
Yeah.
because you literally don't care about your
But in
social
like
interaction.
modern society,
Perception's
it's really
real.
help you.
What?
Perception's reality.
Yeah, his perception was his reality. He's like, I don't care if I'm lying to you because I would kill you if I could to get out of this situation. Okay, focus, Melanie, focus. The pudendal nerve is also responsible for sensory innervation of your junk. It's the pudendal nerve's fault that there are 7 billion people on the planet. You just cut this, no more overpopulation problem. I feel like I could have sex, but have you had a cheeseburger? Because they're amazing. Oh, that'd be interesting. Yeah. They'd have a lot. I mean, I think there's a lot of wiring that goes on in the brain that's already happened. Okay. So now, appropriately, we are going to move to the autonomic nervous system since we were talking about lie detector tests and all that business. This is the last set of notes. It doesn't correlate to what you do in lab, but it does correlate really heavily to physiology. Like you use it intensely in physiology. So before I go any further, you guys have to remember what I mean when I say autonomic nervous system. So remember how we built the nervous system organization on the board? So you guys try to figure out what I'm talking about when I say autonomic nervous system. Am I talking about CNS or PNS? PNS. Am I talking about afferent or efferent? Efferent. And what effectors do you control with the autonomic nervous system? Cardiac, smooth muscle, and you are the smart class today, just so you know. The other people were like, I don't know why you're speaking a different language, but I wish you would stop. Which happens every damn time I teach the autonomic nervous system in anatomy and phys. I don't know. People are like, I don't really think that I need to know this. Okay, so let's talk about the autonomic nervous system. So when we were just talking about this stuff, we were primarily talking about somatic, sensory, and somatic motor functions, which means, it goes to your cerebral cortex or comes from your cerebral cortex. With the autonomic nervous system, this is older functionality, controlling cardiac muscle, smooth muscle, and glands. So you probably won't be surprised that you don't have voluntary control of this. And it's controlled primarily by structures that are way older than the cerebral cortex, like the pons, the medulla oblongata, and the hypothalamus. Pons for respiration, medulla oblongata for cardiovascular function and respiration, and the hypothalamus for global homeostasis. Does that make sense? So you really can't control these voluntarily. Now, can your cerebral cortex sometimes override the functionality of these? Yes, especially if you're an amazingly good liar. So Ted Bundy, sociopath. So he just doesn't have the sympathetic nervous system responses, the fight or flight responses to social interactions, because he doesn't care, right? Yeah. What about a CIA operative who was trained to be able to get through lie detector tests? They're probably not all sociopaths, right? Okay, I mean, there might be some because you'd be pretty damn good at it. But so how do you do that? How do you train, like if you're a CIA operative, like a spy who's like working on location? so that you can get through. Basically, you can train yourself by biofeedback, right? You can like see the response, use your cerebral cortex to try to inhibit what your hypothalamus is telling your body to do. And with enough training, you can get pretty damn good at it, right? I've heard that yogis can do it, and CIA operatives, and people who can walk on coals and those kind of things. But most of you guys cannot do it, okay? Most of you guys your pupils dilate when you lie, those kinds of things that occur. They also dilate when you're turned on. So what if you're turned on and lying? You're like, you're really pretty. I don't know what to think about that. Okay, so this is involuntary and automatic. The cerebral cortex can sometimes override. It's not under conscious control, though. So why do you talk about it if students have a hard time with it? Because if you control cardiac muscle, smooth muscle, and glands, you control the vast majority of the systems that end you up at the hospital, right? Cardiovascular function, cardiac muscle, and smooth muscle controlling diameter of blood vessels. Respiratory function, not diaphragm, not intercostal muscles, but certainly the diameter of your bronchioles is what tissue? What tissue is controlling that? Smooth muscle will be smooth muscle controlling the diameter of your bronchioles. Digestive function is just a smooth muscle and glandular party. That's all that is. Urinary function, kind of the same thing. And reproductive function, that is all smooth muscle and glandular function. Everything from hormone secretion, erection, and ejaculation is all smooth muscle and glandular function. Okay, so the reason that you need to know basic terminology is because you need to know how these things are wired up so that later on, when they start going wrong in whatever your profession is, you'll be able to understand at least how they're supposed to work. So first off, let's talk about the basic anatomy of the autonomic nervous system and remind you that you have learned sympathetic and parasympathetic briefly before, right? So the autonomic nervous system basically is going to wire up to cardiac muscle, smooth muscle, and glands. But what I want you to understand is the heart has two sets of wiring, okay? It's called dual innervation, And so all of these tissues, most of these tissues, have two sets of wiring. And what I'm going to do is I'm going to use one set of wiring under certain circumstances and the other one under different circumstances, right? So what is going on right now is you don't have a quiz, your lab practical's over, you don't have a test, you're not particularly stressed out. Which branch of the autonomic nervous system do you think is probably controlling your heart right now? And what do you think it's telling your heart? Speed up or slow down? Slow down, chill out, okay? So then if a tiger walks in the room, right, then your parasympathetic nervous system says, I can't be used here, right? And then your sympathetic nervous system turns on, right? So what I want you to do now that you know the basic functionality. And by the way, what is your sympathetic nervous system going to do to your heart? Increase. So now we need to find the anatomic routes to get those signals to the heart. You guys ready? Okay. The anatomic routes look super complicated, but they're not that bad. So let's start with what's going on right now. So notice all of these effector organs. All of these effector organs will either have cardiac muscle, smooth muscle, glands, or some combination of them in them, okay? And so please note that this picture and this picture go to the same effector organs. Do you see that? Okay, so what is going on right now in you is that you're telling your heart to chill out with the parasympathetic nervous system. The parasympathetic nervous system has this anatomy. It comes from 4 cranial nerves, and then not a damn bit of it comes from anything until you get to the sacral region, sacral spinal nerves. Okay? So for anatomists who don't care about functionality, a lot of times they call the parasympathetic nervous system the craniosacral division. Does that make sense? Okay. So right now what is going on is you are assessing the situation and figuring out that it's not a fight or flight situation. And then your medulla oblongata, which is in control of your heart rate, is going to send out a signal through cranial nerve number 10, which is vagus nerve, and that's how you are telling your heart to chill out. Okay, so what's going on right now? Cerebral cortex says everything's cool, tells medulla oblongata sends signals out, cranial nerves number 10 to your heart, chills out your heart. That's what's going on right now. Then a tiger walks into the room, and we're all screwed, and I have entirely different physiological needs and anatomical routes to my heart. So now what's going to happen, cerebral cortex says, oh crap, tiger, tells medulla oblongata, there's a freaking tiger. Medulla oblongata says, I got this, and it sends a signal down to the thoracic region of my spinal cord, okay, and then sends that signal out to the heart, yes, and tells it to increase activity. So the sympathetic nervous system comes from the thoracic region and lumbar until number 2. So anatomists who don't care about physiology call the sympathetic nervous system the thoracolumbar region. Okay, so tiger walks into the room, here's what happened. Cerebral cortex, crap tiger, tells medulla oblongata, medulla oblongata sends it out to about T2, T3, and then that goes out to the heart, both sides. Good? And increases cardiac muscle contraction. Okay, so last concept with this is to reinforce for you that I am not telling you that the sympathetic nervous system increases the activities of all tissues. So now what I want to ask is what is going to happen, same scenarios, different tissue. So now we're going to start with smooth muscle of the uterus. Okay? Right now, no particular stress. Which branch of the autonomic nervous system is in control? Parasympathetic. Parasympathetic nervous system, you are going to identify with your cerebral cortex, no particular stress, and then you are going to send that information all the way down to the sacral region of my spinal cord, and then send out an impulse that will cause contraction of the uterus, or at least tone in the uterus. Yeah? If you're menstruating, you can cause contraction. Yeah? That makes sense? Okay, so then a tiger walks into the room. Yeah? When the tiger walks into the room, this is not what you need anymore, and you don't need to spend money on uterine contraction. So what are you going to do to the uterus? Sympathetic stimulation now, okay? Sympathetic stimulation should do what to uterine contraction? Slow it down or stop it all altogether. How do you get it there? This time cerebral cortex says, freaking tiger, sends the impulse down all the way to the lower region of the spinal cord, L1 or L2, goes out, shuts down uterine contraction. Yeah? That makes sense? So last concept on this one is simply, so if you have a spinal cord injury, okay, which branch of the autonomic nervous system will have mostly normal function? Parasympathetic. You are going to lose innervation of your junk, your urinary bladder, and the distal part of your digestive tract. You are going to maintain parasympathetic functionality for the vast majority of your ventral body cavity. Yeah? When you have a spinal cord injury. And if you have a spinal cord injury, depending on how high it is, you can damage a lot of sympathetic functionality. Yeah? So if I have a cervical spinal cord injury, I am going to lose sympathetic innervation of my heart, which is kind of an interesting thing. That means when a tiger walks into the room, is my heart rate going to increase? It's not going to increase yet, but it will increase because it will increase when you dump hormonal epinephrine, adrenaline. So it's like lag time of a few minutes. It doesn't increase immediately because you lost the nervous system connection, but you kept the blood vessel connection, right? Okay, so now, just with that amount of information, you've been able to simplify this, and now you can look at what looks like a super complicated image, and it's not, and you can immediately tell me that this one is which branch of the autonomic nervous system? Sympathetic, and this one is parasympathetic. Yes. So those pictures that look so busy at first get simpler. Okay, so we'll stop there for today. Have a good spring break, guys.
Tell me what these were again, just so I can write them down correctly.
Hold on.